Okay, thank you, and good afternoon, everybody. You've already heard the title. What we're really talking about here is dealing with object motion blur using stabilization elements from off-the-shelf lenses. So as many of us probably already know, optical image stabilization is a feature of a lot of digital single-lens reflex lenses, and they have two main components. There's some sort of sensor in there that detects lateral motion of the camera during exposure, and then there's some moving element in the optical system that stabilizes it in order for a particular point, in presumably a stationary point in the 3D scene, to project its light to the same point on the sensor despite moderate motion of the camera. So these things only deal, first of all, with lateral motion, but secondly, only motion of the camera. There's no instrumentation on moving objects in the scene, and so the systems, when taking a picture of a moving subject like this mannequin head moving from left to right, you still have motion blur. So we're trying to deal with this using the hardware that's already in these off-the-shelf lenses. So here are the guts of the Canon EF 700 to 200 millimeter lens that we modified for the purpose of this project. And in particular, the stuff that we're working with is the output of two position sensors. So these are actually linear sensors. They're oriented orthogonal to one another. And they record the position of a spot of light that's projected from these two slits here. And that position sensor output is used in the general case to drive, to stabilize the image. And the physical motion is created by running current over these voice coils, over these magnets, and it creates motion relative to this stationary metal yoke here. So what we did in order to deal with object motion now is we're cutting out the closed control loop that takes the input from the camera motion sensors, and instead we spliced in a custom microcontroller, which is shown in the blue box here. So the outputs of these analog position sensors here go through a low-pass filter, a 12-bit ADD converter. There's a control algorithm that's going to drive the lens to a position of our choosing, and based on the control algorithm, it drives by pulse width modulation these coil drivers, and physical lens motion is created. So this, basically all of this black part here, including this relatively cheap plastic lens inside, moves laterally and top to bottom along these two orthogonal axes. So this is what the modified lens looks like. We have the microcontroller in this box here, and it's taking commands from a host computer over the serial port. And the type of commands that it takes in particular are these sort of go-to commands, where we're telling it to go to a particular XY position, and we're giving it the amount of time over which it's supposed to carry out this motion. The positions, because of this 12-bit ADD converter, are just these quantized numbers in the range 0 to 4095. And the analog to digital converter runs at 1 kilohertz, so timing here is on the order of milliseconds. The microcontroller is running two control loops for the X and the Y lens positions, and they're basically the same, except for the fact that the Y position has to have this constant offset to account for gravity. Right? Gravity's always trying to pull this lens down. And so there's a little bit of current just to keep it in place. That's interesting. Okay, came back. So with this modified lens, we can do object stabilization in a couple of different ways. One requires that, first of all, we have this real-time lens control, and secondly, that we have real-time real-time estimates of the direction and velocity of motion. And if we have this, then we can take this image that you saw here before and stabilize it so we get a sharp image of the moving object. So what's happening to produce this image is that there's actually a beam splitter behind this lens I showed on the last slide. There's a high frame rate camera that reads off very noisy, very unpleasant images very quickly in order to estimate the direction and velocity of motion. And then that's used to send the stabilizing element in motion to stabilize its projection on the second sensor, which is exposed for a longer period of time. So we've shown that we can do this. It turns out this is quite hard. It's not only do we have to be connected to the computer for real-time lens control, but also this real-time motion estimation is, in order to have good estimation fidelity, it has to be done on a GPU. It takes a lot of power and so on. And also, one of the disadvantages here, of course, is that we're only stabilizing one particular velocity. That is the velocity of the thing that we're estimating its speed. So we've stabilized this thing, but there are a couple of smaller stationary features here. They're on the background, one here and one here. And these are really just pieces of paper. They're slightly optically defocused. But in this image, anyway, there's no motion blur on these things. But when the lens is moved to stabilize the head here, you can't really see it anymore because it's been severely motion blurred, and so it's basically gone. So this certainly can be done. The disadvantages here are that you need a lot of a lot of processing attached to the camera, and also you can only handle this one velocity. So these are the motivations for the motion invariance technique, which was presented originally at SIGGRAPH 2008. There was a 2D extension of that presented at this conference last year. And so I just wanted to give a little motivation here. The objective is really to address these problems that I mentioned on the last slide, that you want to avoid doing motion estimation in the first place because it's a hard problem. And also you want to be able to capture an image in which things moving with different velocities can be reconstructed with good quality. So the conditions here are that the motion blur is both invertible numerically and also invariant to object velocity. The way this is actually done is by imposing this, it's called parabolic motion, although it's actually a motion of the sensor or lens or the entire camera over some line during the exposure. So it's parabolic in the sense of only when you look at position versus time. And so position versus time is shown in the black plot here. The lens starts at some initial position and will end at the same position, but during that time it travels a distance d, comes to a stop, however briefly, and then moves back to its starting position. During this exposure, the exposure time we're calling capital T here, the lens has a range of velocities, which I'm sure are very hard to read, but it starts out here around negative 350 of these quantized position units per millisecond, and ends up at a positive 350, right? So the velocity at the beginning is the negative of the velocity at the end. And the acceleration here is constant. It's positive in this case. It could be negative if we're going left to right versus right to left. And the sort of intuition here is that a particular object in the scene will be moving with some velocity, say here, and at some point in time, in this case around 200 milliseconds of this 300 millisecond exposure, its image will be stabilized, however briefly. And so will every other object moving with a velocity in this range. And so basically every object with a velocity in this range is stabilized for some time, for some short period of time, and not otherwise, but it all sort of comes out in the wash and you get this point spread function that's the same everywhere. So having done this work with real-time motion estimation and having actually instrumented this lens, it seemed natural to try to see if we could do motion invariance reliably on the same sort of setup. So the objectives here of most of what I'm going to be talking about today are first to see if we can reliably implement this parabolic motion in order to get the motion invariant point spread function. And we know that there are reasons why you'd want to do this with a lens instead of other ways of implementing it. In particular, relative to moving the camera, the lens is a lot lighter, and so you spend a lot less power. The thing has less inertia, so in principle you can do this a little bit more reliably. And secondly, the 2D extension of motion invariance was done with sensor motion, and there are some cameras, like Sony cameras, I think, that actually have the sensor instrumented to do this. But if you have a Canon and Nikon type thing, there's already hardware in there to do this, and if it's just a matter of taking it over, let's give it a try. And of course, we want to understand the trade-offs about how much motion there needs to be, what speed the lens needs to move, and so on. So this video that's probably looped a couple of times is showing a stationary mannequin head, a very patient subject that we get to work with. And this is showing you basically the video off of the high frame rate camera that's behind this beam splitter. And you see that during this time the thing shifts. It's actually carrying out one of these parabolic motions of a relatively small distance d But nonetheless, this is what the motion sort of looks like. So to convince you that this really is something like a parabola, and to illustrate some of the control problems that we have here, we took an image where there's a point light source translating horizontally from left to right. And there, at the same time, the lens is executing this parabolic motion in the vertical direction. And so it's actually tracing out, in this case, a parabola. This wouldn't actually be a motion invariant image. It's just to illustrate the parabola. And also a couple of the control issues that you have here. So at the beginning, the lens is in a stationary position, and it accelerates very quickly. And so whereas you'd expect this to be, or you'd like this to be a nice smooth parabola, there's sort of a flat line, and then it gets moving. So it has no velocity at the beginning, so you have to kind of goose it. And anyway, there's this little bow here. And also, because of the commands, as I mentioned earlier, are of the form go to position xy with over a certain time, which gets you control of velocity. We're approximating the parabola here with a sequence of line segments, in this case 14 line segments. And at the junctions of these different line segments, you have sort of these elbows, as shown in the green inset here. So the question that we had is, given these control problems, how well can we approximate the motion invariant point spread function? And analytically, the motion invariant point spread function looks like this here. So we first captured an image basically like you saw on the last slide and compared it to a stationary image. So here's the stationary image. This blue line here is the cross-section through this black to white to black transition. And of course, it's relatively sharp because the thing's stationary. It's relatively well optically focused. This thing, again, the head is stationary, but the lens is doing this parabolic motion, and so there's some blur here. And you get the green curve, which is kind of hidden behind this magenta curve. And what the magenta curve is the fit or the convolution of the blue term with the best fit point spread function of this form, which happens with n equal 44. So the blur is 44 pixels wide. We construct the point spread function, convolve the blue line, and we get this magenta line. So the agreement here between what we would like to see from sort of the ideal motion invariant point spread function and the data that we're actually getting off the sensor are quite close. And it turns out you can do a nice reconstruction of this. In particular, though there isn't a lot of blur in this case, you can make out differences here. Again, the distance here is only 250, which again is out of 4,000. So it's only like 1/16 of the potential range of motion. Now, the real question we wanted to answer was whether we could execute this motion repeatably given various noise sources in the system. Because it's all well and good to be invariant to object motion, velocity of motion, but if the system is not invariant to the various noise sources that actually create the motion of the lens, then you've got a problem. And there are several such noise sources. The ADD converter has its own noise. The position sensor, which again was not one that we selected, it was whatever was in the lens, has some noise. And so, we noticed that there is a fair amount of variability. Anecdotally, as we were doing this, we noticed that it depended in particular on two different parameters. Remember, again, D was the distance that the lens translates over, and NS is the number of linear segments used to approximate the parabola. So relative to those the kinks in the parabola I showed in the previous slide, this kind of makes sense, right? The higher D is, the higher initial acceleration you have to go from the standing lens position, and so that initial bend you might expect to be a bit larger. And again, there were also elbows in the curve as you were changing from one constant velocity to another, so the number of those changes, which is ns minus 1, gives you a number of elbows and things. So we captured for the same stationary target from the last screen 10 images for each combination of a range of distance values and a range of the number of segments. All of them had exposure time around 1/3 of a second. And what we found was that the number of segments really doesn't have a systematic effect on, and I should mention the root mean square error that we're measuring here is essentially the difference, a scaled difference between the green and the magenta curves in this case. So what we found was that there was no systematic effect with the number of segments, but there was one for distance. So this brings sort of the last thing I want to say about motion invariance here, which is that there is this issue with exposure time. So again, the intuition was that the lens is going through some range of velocities and stabilizing things along the way. So the range of velocities over which you achieve this invariance has something to do with how fast the lens is moving. And there's some obvious constraints, like the fact that the lens has to be in motion the entire time, and that the distance is bounded by, if nothing else, the physical size of the lens. So the lens velocity moves in this range, negative Vmax to Vmax, where Vmax is this thing here. And so the problem is that the exposure time appears in the denominator here. And so if you have an increasing exposure time, because you're limited by the amount of light, basically the lens has to travel some position. It has to do it over a longer period of time, so by necessity it's going slower. And so at some point, your range of velocities over which you achieve invariance is limited. And so we did this experiment for an object moving at 1/3 of a meter per second. We have the 300 millisecond exposure, which is slightly underexposed, but the reconstruction is good. 400 milliseconds, which is reasonably well exposed, and the reconstruction is still pretty good. But once we go to 500 milliseconds, this velocity is out of this range, which has been reduced, and so there are significant reconstruction artifacts. So this is something that hadn't been pointed out before. The exact value of the exposure time, half a second is pretty long. The exact value that this becomes a problem will depend on a lot of things, like how far away the object is, how fast it's moving, various things like the focal length and so on. But there is this effect. So I just wanted to end with sort of another cutesy thing you can do with this lens motion, and that's sort of try to replace this wall of lens filters that you might see at a camera store. It seems that whenever I'm going in, I'm looking for this one. And one of the reasons this wall is so big is that there are all these different effects. The filter sizes have to match the size of the lens, and so in principle you might end up toting around this huge bag full of these things. Some of them, of course, can be implemented in software, but only up to a point. And in particular, I was toying with this cross-screen filter, which is shown here. So the image here is from a cross-screen filter. There's a point light source right here. And what you're seeing is this custom effect. There's a diffraction gradient in here. And you get this 4-point star from the cross-screen filter, which people like for aesthetic reasons. This thing costs like $30. If you get it and you decide you want 8 points instead of 4, you have to go buy another one. It costs you some more money. It's kind of annoying. But we can do the same sort of cross-screen effect by just moving the lens and tracing out this star-shaped pattern. It has slightly different properties, which I won't get into all the details of, but just as a high-level comparison, you can, from the same image, get this same sort of cross effect by just moving the lens for 10% of the exposure time, and then leaving it stationary for the remaining 90%. And even though the lens was in motion for 10% of the time, you can still read relatively well. It doesn't look like there's a lot of motion blur here. And the other sort of cool thing is that, of course, the type of filters that you can buy in a store has to do with the type of filter that somebody can sell at a profit, right? So people aren't going to make very customized ones unless you have your own glass shop or something like this. But if you have lens motion, of course, you can do something goofy like, trace out some letters. In principle, we could have done the same thing as we did here, where the motion was only over 10% of the exposure time and then stationary for the other percent. But I just figured, this would give us a sense of what the world looks like through a computational photographer's eye, kind of blurry. So that's all of it. I should mention that our initial round, that in that image you saw with the controller and everything, it looks a bit clunky, and by necessity, all of the images here have been taken in the lab. The camera is fixed to a big tripod. It's connected to a computer. We're going to address this with the next hardware revision. We're going to make this thing smaller, battery-powered, and take the computer out of the loop. And so that should make things a lot more fun anyway. And also, one of the issues, again, with repeatability was that we're implementing this parabola with a bunch of different line segments. And that's really because when we developed the lens, it was mostly for other purposes. And these go-to XY kind of commands are very general. So that's what we started with. But in principle, we may be able to get a higher fidelity motion pattern by sort of hard-coding parabolic motion. We'll see how that goes. And of course, working at Honeywell, we're sort of an industrial company. We work on applications of things, and so the ones that are of particular interest are barcode recognition and iris recognition. And we know that there's going to be some noise because of this, the noisy motion of the lens. What we need to do relatively soon is characterize how much of that noise can be tolerated and still get a nice deblurred, say, barcode image, which sounds like a contradiction, but in any event, a barcode image that can be successfully decoded. And then, we have this thing, and we're certainly interested to think about what else could be done with it. If people have suggestions, I'm certainly interested to hear them. But it's kind of cool to have this thing around in the lab. So that's it, and I'll take any questions. There is certainly time for questions.
Could you say, please, in your experiments, have you shot it from hands, or
no,
how stable it is to real shaking of the hands?
So the camera setup that we have now is, it's bolted to this metal plate, which is on a very heavy tripod. So it's all pretty stationary. That has mostly to do with the fact that this is heavy. So this is a long lens with a 2x extender. There's a beam splitter back here, a couple of different sensors, and all this jazz. So I haven't had the chance, or haven't been daring enough to try to hold it.
Because at the point, if you want to try it in consumer cameras, for example, you have a shake in the hands, and the shake can be not always linear.
Right. So the existing image stabilization, the reason that we started from this lens is that it actually has that feature, and we've broken it for the purpose of putting this microcontroller in the loop here. But in principle, we could have this sort of dual use where it still does what it was originally designed to do, what you're talking about, the camera motion thing, and also does this thing, which is for object motion.
Yeah. So do I understand correctly that you're moving the lens in a parabolic motion like this, and then opening the shutter when the slope of that curve matches the desired velocity?
No. So the shutter is open for some exposure time t, and during that entire exposure time, the lens is in motion. And it's actually moving along a line in 3D space, but it's doing so with its position as a function of time traces out this parabola. The important point of that is that you get velocity. That's this line here. And so there are a range of different velocities that are stabilized all in the same image.
But if you're stabilizing a range of velocities, then any particular velocity would be blurred, right?
Yes. So the image that comes out of this is blurred, and I should have probably been more careful to mention. You capture an image that does have some blur. This is, in this case, very moderate, but you have to apply some processing to that. It's a non-blind deconvolution in this case to get the sharp image. In these, the effect is a bit more dramatic, going from the captured image, which has this motion invariant function, or at least two of them do, to the processed image that's sort of your useful.
Well, how about if you knew the correct velocity, you could just drive the lens at that velocity.
Right, and that's what we were doing here. So we didn't know it a priori, but we measured it in real time, and so this image here is with the stabilization off. For this image, we're doing the real-time velocity estimation and stabilizing that velocity only. Every other velocity is motion blurred, and it's traditional motion blurred through box filter. You have these recoverability problems.
Okay. Okay. Last question.
What would the effect be of nonlinear motion, or how much nonlinear would be before it has any serious deterioration?
Sorry, how much?
If you have nonlinear motion, non-constant velocity, would that deteriorate the inverse direction?
On this example or the motion invariance?
The motion of the person, if it's accelerating
Sure. I mean, in this case, you would have problems. You know, there's oftentimes this constant velocity assumption which holds if the exposure time is short enough. You know, in this case, you certainly would see some motion blur. In the motion invariant case, actually, we don't have this thing instrumented well enough to be able to drive a constant acceleration. So I don't know a good answer to that question.
All right.